Okay, let's start our summary of the whole respiratory system, starting with pulmonary ventilation. And of course, one of the most basic but important concepts we need to understand is basically what is breathing. We know it's air coming into and out of the lungs, but why does it do that? And it basically does it because of the principle we've talked a lot about called diffusion. We know diffusion of water is called osmosis. So what we're talking about now is actually the diffusion of air particles, which we'll be talking about the partial pressure of air later on, describing the difference between the percentage of oxygen and nitrogen and carbon dioxide.
As air moves into and...
So sorry if this video comes on every once in a while. When I touch my computer to point out stuff, sometimes it triggers it to come on, so we'll just have to put up with that. Okay, now the biggest thing is we know diffusion means molecules going from low to high, or where they're greater to where they're less. So we can say the same thing's happening with air, with the air and the molecules of air, whether it be oxygen or nitrogen, because we know it all comes in together, but it's going to go from a high pressure to a low pressure. So the key to getting air into and out of the lungs is to change the pressure. Anytime that we have a higher pressure outside than inside, it will go in. When we increase the pressure inside, where it's greater than the atmospheric pressure of the pressure outside, then we know the air will go back out. Now, understanding how these things happen, we have to understand the anatomy of the lung, which you should be familiar with by now, but we need to understand about the pleural lining, that serous membrane that lines the lungs. We have the visceral pleura, which is the part that adheres to the lungs that's next to it. We have the parietal pleura, which is the part of the pleura that's next to the body wall. And then we have the pleural cavity, the space between the visceral and parietal pleura. We also need to remember that the millions of little air sacs are called alveoli, and they have little cells in them that secrete a lipoprotein that we call surfactant. And of course, what that does, that breaks up the surface area of the water molecules that line the alveoli, so they don't have to totally reinflate every time air goes out of them. A very important physics law is called Boyle's law, which means there's a relationship between the volume and the pressure, because we know the air molecules move by pressure. So if we adjust the volume, it automatically adjusts the pressure. If the volume goes up, the pressure goes down. If the volume goes down, the pressure goes up. So the key is we need to control the volume of the lungs so we can control the pressure of the air inside of them. Notice here the volume's up. In other words, if this were the lung, it would be bigger. Therefore, the amount of air molecules inside of them aren't exerting as much pressure because you have a bigger volume. So therefore, here's our inverse relationship, which again is Boyle's law. And here we see the opposite. Now the volume is smaller and the pressure goes up. So if there's more pressure in here than outside, then these air molecules will leave. If there's less pressure in here than outside, the air molecules will go into the lungs. So the question becomes, how do we make our lungs bigger and smaller so we can make the pressure inside larger and smaller? Because again, keep in mind, if the lung is big, then there's low pressure, therefore air will want to come in. If the lung is smaller, then there's more pressure, therefore the air will go out. So we have to change the pressure between what's going on in the atmospheric pressure and what's going on in the lungs. If the pressure is the same in the atmospheric pressure in the lungs, then air will not move either way. So the question becomes, how do we change the size of the lungs? And that is by changing the size of the thoracic cavity here and changing the diaphragm, because we know our lungs don't have the ability to move by themselves, but since they have that pleural membrane that's adhering to them and adhering to the back of the body wall where these muscles are, then if this gets bigger, then it pulls on the lungs to get bigger. If this gets smaller, it makes a situation where the lungs get smaller. Now in quiet inspiration, which would be like just your normal breath you would take, not a forced breath, or or let's say if you're exercising or something, but just you're sitting there and you're breathing and you're inhaling, which inspiration and inhaling is the same thing. What has to happen for air to just come in through like a tidal volume breath? Well, here we have muscles involved. So we have the external intercostal muscles that are between our ribs, and we have our diaphragm. So when we contract those external intercostal muscles, we get a slight movement, a slight outward movement of the whole thoracic area, and our diaphragm drops. So what that does, the movement out and the dropping of the diaphragm increases the space on the inside. Therefore, it increases the size of the lungs since the pleural membrane is adhering to both of them. So again, it's dependent on the contraction of both the external intercostals, which makes everything rise a little bit, and the flattening contraction, which flattens the diaphragm, causing it to go downward. But what the whole reason we're doing that is to increase the volume in this area, which makes the lungs get bigger. Now, quiet expiration, which is the same thing as exhaling, and again, this is done during a normal breath, during a tidal volume breath, then all we have to do really, it's passive, all we have to do is relax the muscles that contracted. We relax the external intercostal muscles and we relax the diaphragm. And when we relax, things go back and get smaller. The diaphragm raises back up, which decreases the volume inside, and the external intercostal causes everything to lower, which again decreases the size inside. So whereas quiet inspiration is active by contracting the muscles, quiet expiration is passive just by relaxing these muscles. Okay, well, how about if we take a deep breath, a deep inspiration and a deep expiration? What do we have to do this time? How is that different than a quiet breath? So what we're definitely going to have to do is use more muscles, and then even in expiration, muscles are going to be used in that situation. Okay, we're still going to use our external intercostal muscles and diaphragm, even though we may cause them to contract more forcefully according to how deep a breath we're taking, but we're also going to add in a neck muscle called the scalenes and the sternocleidomastoid muscle, because this is going to further lift up on the whole thoracic area, making it even larger than just a normal breath. Because the larger it is, the lower the pressure, the more air is going to want to come inside. Whereas a quiet expiration was just a relaxing of the diaphragm where it went back up and the external intercostal muscles. A deep expiration, when you're really pushing that air out, you're going to also use your internal intercostals, which are more inside and kind of overlap some of the external intercostals. And you're also going to use your abdominal muscles, especially these oblique muscles. So your rectus abdominis, your external oblique, internal oblique, and transverse abdominis also get involved, and what they do is they compress everything inward to the point that it really makes this whole thoracic area smaller. So between this active contraction of the internal intercostals and the pushing of this, plus the relaxing of the diaphragm and the relaxing of the external intercostals, then we're going to make this as small as possible, which is going to increase the pressure. Therefore, when we increase the pressure inside over outside, then we force the air back out. Okay, this brings us to our next major concept, the inside pulmonary, inside the lung pressure changes that are occurring because of these size changes. Now, the muscles created the size changes, and that affects the pressure changes, but let's look at the pressure inside of the lungs, inside the alveoli, and talk about what was happening as our sizes got larger and smaller. Now again, look at what we've got. We have our parietal pleura, which was the part of the pleural membrane up against the body wall where the muscles were and up against the diaphragm. We have the visceral pleura that's adhering to the lung itself. It's one continuous membrane, but it does have the two different sides. And then we have the pleural cavity, the space between the two different sides of the pleural membrane that has fluid, but it also has its own pressure, which we're going to talk about a little bit later. Now look at our chart here, because this is atmospheric pressure, which is at sea level. We can measure it to be 760 millimeters of mercury. But since we're not always at sea level, that's our baseline reading, since we're not always at sea level, we will call wherever we're at, and whatever the pressure is wherever we're at, we'll call that zero. Now if we were at sea level, then if we kept the pressure in our lungs at 760 millimeters or zero, if we're at a different place, that means that air is not going to go in or out because it's equal. And if we have equal pressure on either side, then there's no need for it to go in or go back out. So if we want air to come into the lungs, what we're going to have to do is we're going to have to drop the pressure inside below atmospheric pressure. And so if we drop it below, air will want to travel inside. If we want air to go back out, then we are going to have to increase the pressure inside higher than atmospheric, because if it's higher here than outside, it will go from higher to lower. So remember, it's all based on the principles of diffusion, going from a high to a low concentration. In this case, the concentration is of air molecules. Notice in this picture, this is dropping, meaning the pressure inside the lungs is now dropped lower than the pressure of the atmospheric pressure outside. Therefore, air has to move from the high outside into the lungs. So this is definitely going to be an inspiration in bringing air in, just because we drop the pressure difference by changing the size. Now, again, if I'm making this a lower pressure, then what I had to do size-wise is I had to make the lungs bigger by contracting the muscles we talked about before. Now notice we dropped the pressure here, but as air started filling it back up, then the pressure actually started rising again, okay? Because again, we dropped the pressure so the air would want to go in, but as the air goes in, then it starts building that pressure back up until it's equal with the atmospheric pressure. So at this point, no air is going in or out. Now notice this, since we're at that point where air can either go in or out, now that the lungs are full of air, so what we want to do is increase that pressure inside. So how do we do that? We make the lungs smaller. That starts increasing the pressure, and air starts going back out. Now, once we get to the point where air starts going back out, then the pressure starts lowering again. It's still greater than atmospheric pressure, so it still goes back out. So again, we've increased the pressure. Air starts going back out. As it goes back out, the pressure starts dropping again until it reaches basically atmospheric pressure, where air is neither going in or out. But then this starts repeating. We literally start dropping the pressure again by making the lungs bigger again in a tidal volume of breathing.
The intrapulmonary pressure.
Now, whereas intrapulmonary pressure was the pressure in the lung, particularly inside all these millions of alveoli, remember, again, we have our visceral pleura that's adhering to the lungs. We have our parietal pleura, which is adhering to the thoracic wall. It's back there next to those intercostal muscles and ribs. And then we have this cavity between this portion of our pleural membrane and that portion of our pleural membrane. And it does have fluid in it, but it also has a pressure gradient that's called the intrapleural pressure. Now, if you will remember, we talked about how we create suction is we have two different spaces with different pressure differences, and as long as I can keep the pressure differences, it creates a suction. So what we have to understand is that the pleural cavity has a lower pressure than the alveolar cavity, so when this drops, this has to drop even lower. When this rises, this can rise, but it will always be a negative pressure compared to the outside pressure. Okay, we maintain this pressure in here due to the surface tension of the fluid. In other words, every time we exhale, these want to collapse a little bit. They don't totally collapse because of the surfactant, but they collapse just enough to where it causes since the lungs are elastic, it causes the lungs to move inward a little bit when we exhale and move outward a little bit when we inhale. Okay, so it is in one of the fibers here are elastic. Some diseases cause them to be more rigid, and it loses some of the elasticity. But in a normal lung, there's elasticity. Also, we have the lungs moving outward, the thoracic wall moving outward while the lungs are moving somewhat inward. That creates the space here and creates the actual pressure within the space. So we have these three factors that are creating the intrapleural pressure.